Recording is already going. That's very good. The lighting is very harsh today. Okay, I think this is better. Any questions before we start? Why are there so few students so far? Only seems to be 30 students. Are you guys running all late, or is it? Oh, okay. Yeah, thanks for telling me. I was afraid it was my teaching, but then it might be the midterms. Okay. So we'll start right where we left off. And remember that yesterday, so yesterday what happened was that we observed if we have a basis, every vector in the vector space has a unique representation as a linear combination. And I have defined the coordinates of a vector in this basis as just the coefficients. And because there are n coefficients in an n-dimensional space, this coordinate vector will be an n-tuple. And an n-tuple just naturally is something that lives in Rn. So what I'm doing today is a direct continuation. It is this theorem, namely that if we choose a basis, this assignment for every vector to get an n-tuple is, well, it's a function. It looks like a function. It takes an input, gives an output, and so we're defining this as a transformation, denoting this gamma super alpha. So like this is superscript alpha. And this theorem claims that this is actually a linear transformation. And the superscript is very important because this alpha, the basis alpha is of course very important to this transformation. If the basis changes, then this will be different transformations because the linear combination depends heavily on the basis. Any questions about the notation? Does that make sense? So I'm basically not saying anything new. I'm just saying something about, I'm just making the assignment from a vector to its coordinate vector formal. I'm just fluffing this up. I'm just introducing notation and I'm using fancy words, but it's the same idea as before. When we have a vector and a basis, there are these n coefficients, and that's what I want to extract. All right, so we want to prove this is a linear transformation. And this isn't actually too hard because there's just two things we need to check for a transformation to be linear. So what we start with is we just pick two elements in the vector space. And then they have a linear combination in terms of alpha. So let me call this v equals v1, alpha 1. And alpha, it's very, I'm aware that alpha used to be scalars, but for notational purposes, I think it's good now to use Greek letters for bases. Oops, this wasn't intentional. So let me denote the elements in alpha, which know the basis, just by alpha 1 to alpha n. So there are n elements in the basis, meaning that it's n-dimensional, as I said there. Okay, so we have for both alpha v and w, we have a linear combination in the alphas. And I think it's just convenient to denote the coefficients by v1 to vn because they are the coefficients that make up v. Okay, w has this similar linear combination in terms of the alphas. And this means if we're given this, or if we just write them as these combinations, then this means that their sum v plus omega w is equal to v1 alpha 1, v1 alpha n, and then we list all the terms that make up w. But we can reorder this because summation in a vector space is commutative. So what this means is we'll just get v1 plus w1 as the coefficient of alpha 1, and we'll get vn plus wn as the coefficient in front of alpha n. But this means now the transformation gamma alpha just reads off the coefficients. So this means by definition, gamma alpha of v plus w just picks out these coefficients of the linear combination. So this means what we get here is the n-tuple v1 plus w1, v2 plus w2, vn plus wn. But this is just an n-tuple, and in Rn, an n-tuple, we know what summation we usually use to make this a vector space. So I could have been more precise here, saying which operation actually we want to use as a vector space structure, because that will influence the transformation. So what I'm writing here is I'm just decomposing this into the sum of two n-tuples. But notice now that because v and w have exactly these linear combinations, these tuples are precisely the coordinate vectors of v and w. So what I can write here is gamma alpha of v plus gamma alpha of w. Any questions so far? I'm running out of space, so I'm gonna shrink this a little bit. No questions. Okay, so this is half of the work for showing that something is a linear transformation, and now we can also pick. I mean, we don't have to pick again. We can use the same v, but now maybe pick c in R. Then it's clear that c times v is the same linear combination, only that each coefficient is multiplied by c. And so this means if we now compute the coordinate vector of this combination, it's not nothing hard. You just pick out the coefficients. That's literally all we do. So now we take these coefficients. And so this means that gamma alpha of c times v is the coordinate vector v1 times c up until c vn. But this now, again, now we use the scalar multiplication in Rn to write this as c times the vector v1 to vn. And if you look at the original linear combination that describe V, then you can see that this is exactly C times gamma alpha of V. And this concludes the proof that this is, in fact, a linear transformation. Yes, so this the alphas here are the basis vectors. I want to use Greek letters for bases from now on. I think it's at least for me, it's faster to type when I do the lecture notes than a calligraphic B. And this means that the alpha 1 to alpha n are going to be the basis elements. In basis alpha. So we've shown that this is a linear transformation. But I've said even more here. It's even more true that this is an isomorphism. I'm going to skip this for now, but we're going to come back to this probably later, or I'll just leave that as an exercise that you can think about why this is an isomorphism. But remember that yesterday I've already taught you something about isomorphism, and the intuition here, the map gamma alpha is identifying every n-dimensional vector space with Rn. So no matter if you have two different vector spaces of the same dimension, they both have this map as long as they have a basis, or as long as you choose a basis. And we've seen that you can always choose a basis. So the idea is that because you have this isomorphism, whatever you do in V, whatever operation, whatever transformation you consider in V, you can also do now in Rn. So this gamma is rigidifying this. And this is pretty amazing, because you have to imagine how many different vector spaces there might be out there, and how many examples I've shown you 2 weeks ago or 3 weeks ago. And now it turns out that as soon as we fix the dimension, there's only one identification. So this is almost like disappointing to us, because we thought there's so many vector spaces, but it turns out they're all the same. There's only one for each dimension. So we're going to see later, and actually today we're going to investigate this more, and we're going to exploit this more, the idea that we can just work with Rn if we have an n-dimensional vector space. But the key is that an isomorphism uniquely identifies a vector with an n-tuple. And in fact, I think, no, I mean, this is, the rest should be clear. We've already said it as, I just forgot that we already had a theorem last week that said that the linear combination is unique for a basis. And this uniqueness exactly gives us an isomorphism, because it means that it's injective and surjective. So you can convince yourself that this is that this will work out. Okay, so Andrew wrote in the chat something about degree n polynomials, but remember that the dimension of P and R is n plus 1. So your question is correct, except you need Rn plus 1. We're going to get to this later today. So I'll give you now 3 minutes to discuss this. Suppose you have a transformation T, and I'm not telling you what it is. I'm just telling you what the value is of these 3 vectors. And since we work on the vector space of polynomials, these polynomials are vectors. So I'm giving you these 3 pieces of information, and I want you to find T of x. Yes, T is linear. I didn't write this, but this is very fundamental. This is very important. So this is linear. All right. Any ideas? How can we approach this? Idris.
So what I did was I recognized that since the transformation is linear, you can split. Since I know that t1 is equal to 1, you can split the very top one into t of 1 plus t of x squared, and then you can solve for t of x squared, and that's I got 4. Yeah, 4. And then you can do the same thing for the second one. So t of x minus t of x squared is equal to 3, and I got t of x is equal to 7.
Yes. Notice that this is not. Oh yeah. This works. So what you're doing is you're using the fact that is linear, and you can rearrange. You can, if you add and subtract these ones, then you can interchange summation and application of t.
Yeah.
So let me write down a slightly different way, because I think this is also helpful. But yeah, this is completely correct. Thanks. So what we want to do is we want to re-express the vector x, the polynomial x, in terms of the polynomials that are given. So what we notice is we can use this one, x minus x squared, but then we have this x squared which we don't want. So we need to add x minus x squared, and now this will cancel out. Sorry. I mean, we need to add x squared uh, 1 plus x squared, the first element, and then the x squareds will cancel out. But now we have an additional 1, so we can just subtract 1. So notice that I've rewritten x, the polynomial x, in just by using different polynomials, and each of them we know the value of t. So this means when we write t of x is equal to t of x minus x squared plus 1 plus x squared minus 1, then we have not changed the argument, and so this is why these terms are equal. But now because t is linear, we can write this as t of x minus x squared plus t of 1 plus x squared minus t of 1. And now these values are given because this is what we know about t. So this means this is 5. No, sorry, this is 3 plus 5, and this is minus 1. So this is 7. So now you might be wondering, was it just lucky that this information given above here is enough to find t of x? Does it work for every other polynomial? And the answer is, well, as you observe in this procedure that we just did to find the answer, what we need is to express x in terms of the vectors that we know the value of under t. So this means if these vectors that we know the value of under t are a basis, then we certainly know that there's some combination for every vector x, for every vector in the vector space. And this is actually the content of the next proposition. It says that the transformation is uniquely determined by its values on elements of a basis on V. So I'm basically just making the last discussion more abstract. So let me quickly write down the proof. So if we suppose that alpha with vectors alpha 1, alpha 2, alpha n is a basis. And we know TF alpha I for all I from 1 to n. Well, then for any x, or for any v, in v, we just do exactly what we did in the discussion. We first use the fact that v has a linear combination expression in terms of the alphas, because it's a basis. That's the whole point of why we wanted to have a basis, or a basis in vector spaces. So to compute T of v, we first express v in terms of a basis. So this is going to be v1 alpha 1, v2 alpha 2, vn alpha n. And here for some unique coefficients v1 to vn. That's part of the previous work that we did in the last week. And then because this is linear, in this week's lecture slides that we're going to start after this, I actually was very careful to add the word linear to every instance of transformation in the notes. But we need this linearity. So this is v1 times t of alpha 1, and so on, and up until vn times t of alpha n. And by assumption, these are known. So we've shown that it's enough to know the value of t on the basis elements. And this should be the last slide, the last page. Any questions before we move on to the next set of slides, week 4? Okay, so let me erase this thing. This should not be here anymore. Neither should this or this. Yeah, and then we can start with the lecture of today. So today we're going to continue transformations. We're going to talk about, in particular, in this section 2.2, we will focus on one important bit, which is encoding transformations as matrices. So we've just finished talking about how we have for every vector a coordinate vector, and this depends on a basis. And this helps us to encode the information of a vector completely in an n tuple of numbers. Now, the cool thing is we can further exploit this, and we will observe, and that's the goal of the first lecture today, the first half, that we can encode the information of a transformation entirely in a matrix. Also, 2 announcements. So we'll hopefully get today close to the end of this content. And next week, I believe on Friday, sometime next week, there's the first midterm test, and I'm gonna do the last hour before the test. We're gonna have a review session, just to go back and recycle some things. And if you want to review anything in particular, then please send me an email requesting the content. Otherwise, I'll just go through everything that we've had so far in an hour and try to remind you of the most important things. Oh, sorry, I forgot to put up the lecture notes for today on the website. They are on GitHub. I pushed into GitHub just slightly before the lecture, but I'll add them later to Quarkus. Okay, the other announcement is from now on, I don't want to talk about, I don't want to say finite dimensional anymore. So everything from now on is supposed to be finite dimensional. And let us start with an example so that you can observe a pattern in this before we actually go to the rigorous setting. And then you can always think back to this example. I think that's helpful. So we just finished the last content, the week 3 content, with observing that it is enough to know a transformation on the basis elements. Well, now suppose that I tell you for this case of R2 that T has that T sends E1 to the sum of E1 and E2, and it sends E2 to 2 times E1 minus 2 times E2. What kind of data does this involve? So this really involves coefficients here. So it's +1, +1, +2, and -2. So one could say that all information that we need about T is encoded in these 4 numbers. And we can write this suggestively as A11, A12, A21, and A22. And in this case, this is going to just be 1, 1, 2, and -2. Now, you can think of Aij, the number Aij in this matrix. You can think of them of how much Ej in TFEI. So if you look at this, the number AI2, say, is the number that we have in front here. So it's the contribution of E2 to the image of E1. So this is the first index and the second index, and the first index refers to the EI in TFEI, and the second index J refers to how much contribution Ej has. Okay, so now we've seen after this that when we want to compute TFV, then what we need is we need to find an expression of V in terms of the basis. So we need to find T V1 E1 plus V2 E2. And then we use linearity to write this as V1 times TFE1 plus V2 times TFE2. And now we know that exactly E1 is TFE1 is E1 plus E2. And TFE2 is 2E1 minus 2E2. So if we sort this by basis element E1 and E2, we get that this is V1 plus 2V2 times E1 plus V1 minus 2V2 times E2. Okay, so this is the left-hand side, and I've tried to remain on the left half of this page. I almost succeeded. Now, if V has this, if V can be written as V1 E1 plus V2 E2, then this means that the coordinate, so coordinate vector, let me call this alpha. The coordinate vector of V in this basis is V1, V2. Now, the coordinate vector of the result, let me rewrite this in the bottom. So from this, if you compute the coordinate vector of T of V in the same basis alpha, because there's just one basis, because V is W and they share the basis. So there's no two bases for now. Then how do we find this? Well, it is precisely just the coefficients in this combination in terms of the basis. So we have here V1 plus 2V2 yeah, sorry. I think someone in the I just noticed that I set up this problem in the wrong way. But we'll see in a second why this is minus 2 V2. Okay, so if you wanted to use this isomorphism to Rn, this identification with just the simple n-dimensional vector space Rn, then we could transcribe the data of V in terms of this two-tuple V1 and V2. We could apply the transformation in terms of the vector, and we would get another two-tuple V1 plus 2V2, V1 minus 2V2. And yes, indeed, I think I do want to transpose this. So sorry for the confusion. So then this red thing is wrong, but now let's compare these two tuples. So the coordinate vector of the initial vector and the coordinate n tuple of the result they are precisely correlated by a matrix multiplication of this matrix. So this means that that if we have 1, 2, 1, minus 2 times the coordinate vector v1, v2, then we will get v1 plus 2v2, v1 minus 2v2. So this means going, and now I want to wait drawing this. No, let me wait drawing a diagram. So this example should just suggest to you that we can encode a transformation in terms of a matrix, and applying the transformation to a vector and then getting back a vector is the same as applying the matrix by multiplication to an n tuple representing the vector, and then we get back an n tuple which will represent the result. Any questions? Okay, and to make this to go a little bit more to the formal side, the abstract side, you might wonder, how do we get such a matrix? If you're given a transformation, how do we compute the matrix that does the job that we just found that we can perform? Well, I've wrote down an algorithm, and this is going to be very helpful for questions later, because this will boil down exactly the steps you need to take each time you want to find the matrix of a transformation. So if you have a transformation which is linear, and we have a basis for the domain and the basis for the target, and this is going to be the same for the rest of the lecture. So we're always going to have the basis alpha in the domain and the basis beta for the target. Then this matrix that we compute can be found in terms of its columns. So we have to, the first step in this algorithm is, for each element in the basis in the domain, each alpha I, we want to apply the transformation. And I'm assuming here that the transformation is given as some formula. So what you need to figure out in each case is what does it mean to apply T? And that will depend on the exact example. We're going to have discussion in a second where you can see what I mean by this. So now that you've found vectors T of alpha I for each element in the basis alpha, you'll have just n different vectors or m different vectors in W. Well, how do you get a matrix out of this? Because W has a basis, you can associate to every vector, in particular these m vectors T alpha I, we can find their coordinate expression. That's the next step. Find the coordinate vector of these m vectors, and then you'll get m n tuples. Notice that m and n are different. So these will look like just n tuples. It's just going to be, so the size of them is going to be n, and you will have exactly m of them. And the last step is assemble these coordinate vectors as columns in a matrix. So you would just write A, and you're going to write these as columns. And then the claim is, well, that's not part of the algorithm, but we're going to see later that this is exactly the matrix that we're looking for. So before we define this abstractly and we prove things about this, which we're going to do later, I want you to discuss the following. Now the vector spaces are P2R and P2R, and we have a basis for this. Case, again, we take just the basis of monomials, 1x and x squared. And the transformation that we've seen before, and we've actually shown that it's linear yesterday, is d by dx. So we take the derivative of a polynomial. And I want you to compute exactly this matrix, the matrix representing this transformation. I'll give you 3 minutes to think about this. Any questions before we do this? I mean, is the algorithm clear? Okay, can we discuss the results? Do you have any ideas? Partial solutions. Okay, so Andrew has as a solution. Can you tell me what you did step by step? So this is your suggestion.
I just took the first row to be 1, the second row to be x, and the third row to be x squared. And so first I looked at where 1 lands after the transformation. So 1, 0, 0, that will be just 1. It should land at 0, 0, 0.
Yes, so we apply, so these are the 3 elements in the basis, and now we just apply the transformation, which is d by dx this time.
Yeah, so 1, 0, 0 should land at 0, 0, 0, and
okay, 1 second. So I want to do this step by step and slow this down a little bit. So this is step 1, right? So we now at step 1. Let me just color code them for 1, 2, and 3. So can we finish step 1 for all the elements alpha 1, alpha 2, alpha 3?
Yeah, sure. So x would land at 1, and 2x would land at x squared should land at 2x.
Yes, thank you. Okay, so this is step 1. I just want to like make this an exactly analogy to the algorithm so that we know what we do. Okay, so this is the first step. Anyone else with, or do you want to continue with step 2?
Sure. So step 2, I sort of put them into vector form.
Yes, so we want to find the coordinate vectors. For, well, yeah, for what we just computed in 1, exactly. What do you get?
So 1, 0, 0 would become 0, 0, 0.
Okay, let me write this in this way so that we know that this is the coordinate vector to the result d by dx applied to 1, which is 0. And this has just the coordinate vector 0 because it doesn't take any of the basis elements in the combination. Okay, next one.
Yeah, it's essentially the same step, but in the column vector form, you get 1, 0, 0 because you just get 1.
Yes, precisely. Okay, so so this step from here to here, it just means that 1 is equal to 1 times 1 plus 0 times x plus 0x squared. And we've exactly used these coefficients in the combination and written them in a vertical vector. Okay, and the last one.
Oh yeah, yeah, and it's essentially the same step, but for the column vector, you end up with 0, 2, 0 because it's 2x.
Yes, precisely. So when we apply this d by dx, this transformation to x squared, we get 2x. And then when we want to find the n tuple, we express x squared, so 2x, in terms of 0 times 1 plus 2 times x plus 0x squared. These are the coefficients. And then we just write them as a vertical column, and we get 0, 2, 0. Correct. And now the last step, step 3, just says that we should assemble these in the right order, in the order that we found them inside a matrix. So this means we'll obtain a matrix consisting of 0, 0, 0, 1, 0, 0, and 0, 2, 0. Okay, again, this transposition thing happened. I'm not certain right now whether you're correct or I'm correct. But I anyways wanted to do a sanity check. So let's do this. The claim is now that when we have a polynomial, we find its coordinate expression first. We multiply this coordinate vector with this matrix A, we should get the coordinate expression of the derivative of the polynomial. That was a long, very long sentence. Does that make sense to everyone? So let's test a polynomial. Actually, we can just do a general polynomial. P of x is equal to a plus bx plus cx squared. I mean, then we do them all at once. Now, if we, let me start writing this in a suggestive kind of format. So when we apply gamma alpha, remember that's the thing that extracts the coordinate n tuple, we will get A, B, and C. Now, when we apply the matrix A, what we'll get is 0, 1, 0, 0, 2, 0, 0, 0. And we multiply this by ABC. Then what we end up with is B, 2C, and 0. Is that correct? Do you guys agree? And if you apply the transformation, so this means we apply d by dx to this. Well, d by dx. Let me just save the time, and this is b plus. Well, I can just write d by dx p of x is equal to b plus 2c times 2x. And now let us observe that if we want to write this in terms of the basis, so b plus 2x is b times 1. Oh, sorry, 2c. 2c times x. So this is 2c times x plus 0 x squared. We have the coefficients b, 2c, and 0. And this is exactly what we find here. So we've now seen, we can now draw this arrow to say, well, the resulting polynomial will have a coordinate vector b, 2c, and 0. Any questions? So yeah, this should be the transposed of what you suggested. But that's, I mean, it depends on the basis, and here the order is 1x squared. Your answer would be correct if the order was different. At least in one of them, I think it would be different. Yeah, but yeah, this is the answer. Okay, it's almost time for the break. Any questions? I want to go one step further before we take the break, because now I want to actually go to the proper definition, and this is the final version of what we're going to work with. But I think the algorithm was helpful in the beginning, because there's no point in just screaming out some words, some fancy terms that you can't work with. But now that we've seen how this thing works, this machine operates, we can say that, well, for any transformation T, which is linear, and again, bases alpha and beta of V and W, we define something called the matrix of the linear transformation T. And it's not a surprise that this is exactly the matrix that satisfies the property that when we go to the coordinate point of view of a vector, then we want to apply this matrix by matrix multiplication and obtain the coordinate vector of the result of T. So I've drawn this this kind of this diagram before, but if we have V, in the vector space V, and the transformation T that goes to W, then what we can do is we can find the coordinate expression gamma alpha, and this will be just a vector in Rn. And when we have a result T of V in W, we can again find the coordinate expression gamma beta. This time alpha and beta are different because they might not be the same all the time. And this will land in Rm, just as I mean, M will have to be the dimension of W and N will have to be the dimension of V. And now the transformation goes V to W, but a matrix, if we multiply a matrix, it doesn't really take vector, it doesn't really take any vector, but it has to be an n-tuple. So we can think of the transformation, the matrix of the transformation T alpha beta to be exactly taking the coordinate vector. So this is going to be taking V in the coordinates, the basis of alpha, to the coordinate n-tuple of T of V in the basis beta. So this going from the left to the right hand side, if we cover the bottom half, then this is, I mean, I can't cover this with my hand right now because it won't make a difference. But if we just look at the top half, it's vector space to vector space. We've used this basis idea before to encode everything in a vector space as in Rn. And now this is exactly what I promised you before, that we're gonna do the same to transformations. So what we've done now is we have encoded a transformation in terms of the n-tuples of vectors, going from one n-tuple to an m-tuple. So the idea is that this is exactly this matrix alpha beta multiplied with the coordinate V alpha. Any questions? Yeah, the sub and superscript here is that we always imagine, like, we always want to go from bottom to top. So this is the starting point is alpha, and then the superscript is the one in the target. Okay, let me just check what's going to be next. Yeah, okay, so I think this is a good place to pause. We'll just reconvene at 2:10. That's in 5 minutes. So I'll just let this here. If you have questions, go ahead. Otherwise, I'll continue in 5 minutes. So we're live again. There's one thing I want to add to this discussion and this picture. So I've told you before that this gamma alpha is an isomorphism. And this is really cool because this means we can also go backwards. So there's the other way around too. So we can do a gamma alpha inverse. Now, and what is this gamma alpha inverse exactly? So the gamma alpha inverse goes from Rn back into V, and it takes an n-tuple, say x1 to xn, and it kind of results this in as a blueprint. So think of this as a blueprint of a vector. This is just giving you the coefficients. And then what the gamma alpha inverse is doing, it assembles this into x. So gamma alpha inverse of x1 to xn. It just has to find the combination with these coefficients, but that's not hard. You just write x1 in front of alpha 1, and you just build the linear combination with the coefficients x1 to xn. And this is going to be an element in V. So this is going back. You just assemble the n tuple to a vector. So you could also start with an n tuple on the bottom left. You could build it, then apply t, and then decompose it into an n tuple again. And that's the same thing as just multiplying the n tuple with this matrix. I don't know if this is confusing or if this is helpful, but if you have questions, please do ask now. Otherwise, I'll just go on. And I mean, we're going to use this now a few more times because this first lecture really is about, this first half is really about this idea of transformations and matrices. So that's the key idea in this first part. Let's just do this discussion right away without thinking about it, because I think it's easy enough. What is the size? I mean, of course, the size. What does the size of the matrix associated to a transformation depend on? And what is the matrix of the identity transformation? Yes, Andrew said dimension. Can you explain this?
So I was thinking the transformation matrix should have the same dimension, should have the same number of rows and columns as the dimension of the domain and the codomain.
Yes, precisely. Let me just make sure that I get this right, because this is easy to confuse. So T alpha beta should be in MAT m comma n. Remember that the first one is the number of rows. So it always goes down first. And then the second one is the number of columns from left to right. And so if we have T going from V to W, then the number of columns has to be the dimension of V, if I get this right. So the dimension of V has to be n, and the dimension of W has to be m. And the reason that you can, the way I remember this is, if you go from V and W to their Rn representations, their coordinates, the tuple formulation, then you will have to be able to have an n tuple. So this is an n tuple representing a vector in V, has to be able to multiply with this matrix T alpha beta. And so this size has to be n as well, so that the definition, that the multiplication is well defined, and the resulting matrix, the resulting vector of an m cross n matrix times an n vector is going to be a vector of size m. So this way you can remember that the matrix is always m cross n. So this is m cross n for dimension V is n, and so it's the opposite way, that m cross n goes from dimension n to dimension m. Okay, what about the second part? Someone tell me what is the matrix of the identity operation. Yes, the identity matrix, exactly. This is, oh, no, what did it undo? Yeah, right. So, I mean, if we do the algorithm, then you can see that if we apply ID to every basis element, alpha I, where alpha is the basis, this is going to be alpha I, and then the coordinate expression, I mean, this is the algorithm, the second step of the algorithm. The coordinate expression of alpha I in its own basis is going to be just a vector 0, a vector with zeros, 1, 1, and then zeros again, where this is the ith position. I'm running out of space here. Ith position. And then if you assemble all these vectors with 1, 1 at the ith position into columns, then you're going to have exactly a diagonal where the diagonal is 1 along the diagonal. Yes, that's what Gen C just wrote in the chat. I don't want to write over the example, but I think I have to. Is there some other way? Yeah, let me just shrink this one more attempt. Then I'm also going to shrink this down. So from this, as I just explained, we'll get that IDV from alpha to alpha is just this matrix. Okay, let's do one more example before we move on with probably the next. Oh, there's so much more than I want to talk about. Okay, do you want to do another example or move on? Did you have enough examples, or is it still unclear what we? Okay, we also have two different. Okay, the next one decides. Okay, let's. Oh, geez. Let's move on. And if there are questions, we can look at this at the end if we have more time, or in the review session, we have something to talk about. So we're definitely going to do this at some point, but for now, maybe let's move on. I mean, just apply the algorithm is the. So we'll do this later. Okay, so I just want to maybe not a discussion, but maybe just say a little bit about the other way around. We've talked about how a transformation gives us a matrix. I just want to emphasize that a matrix gives us a transformation too. And I've already said a lot of things that kind of hinted at this. But so if you have a matrix, yeah, this is just A in MAT NM. Sorry, N and M are never the same order. Like N might come first or M might come first. It doesn't really matter. Then you can think about this as a transformation, and the domain is going to be Rm, and it will go to Rn just by taking an n tuple. So it's going to take x1, xm to the product of A times x1 to xm. And as I explained before, this product A times an m tuple is going to be, this is going to be an n tuple because A is of size n cross m. And Now, the important bit is, well, this gives us a function from Rm to Rn, but the important bit is that this is linear. So let me write this on the right here. This is linear. So the assignment of x going to ax, a times x. And actually, let me call this t sub a. So t sub a is the transformation. That is built from a. And this is linear because exactly of two things that we need to check. We need to apply a to x plus y, but we know that this is a times x plus a times y. This is just a fact from matrix multiplication. And we also know that a times cx is equal to c times a applied a multiplied with x. And these are the two things we need to check. Now this is just because it's just between Rm and Rn. But remember that Rm and Rn are exactly the prototypical vector spaces of these dimensions. So if you have any, if you now continue this idea, and then say for any vector spaces v and w with bases alpha, beta, we also need that the dimension of v is equal to m and the dimension of w is equal to n. We can just define a transformation between these by just applying the gamma inverse, the inverse coordinate transformation. So this means if we want to define a transformation T for the matrix A, then what we do is, well, because Rm is isomorphic to V because they have the same dimension, we can just get a no, sorry, I don't want to talk about the inverse. I want to talk about this direction. This makes more sense. So the question is, what is TA of V? Because this is really what you need to define for a transformation from V to W. Well, you just take its n tuple first, m tuple, then you multiply by A, and you get an n tuple, and this can be built into a vector V by doing the inverse, inverse of beta. So this discussion really just shows that a matrix gives us back a transformation, and because it's already very late, I want to cover some other stuff. Let me just summarize this by saying that we've now identified matrices with transformations between finite dimensional vector spaces. And the operations, the algorithm gives us a way to get a matrix from a transformation. And this discussion just tells us, well, we can also get a transformation from a matrix, and these are inverse to each other, these operations. So if you were to try to find the matrix representing T sub A with this algorithm, which would be, I mean, you just went from matrix to transformation, you want to go back, you will get back A. Only though if you have the same bases alpha and beta, that's important. Any questions? Okay, yeah, I mean, we've basically done the proof that doing the proposition. So this is just what we've done above. This is enough to prove this. Yeah, for some reason I've been really heavy on abstract notation in this lecture. Yeah, let's skip this discussion for now. Maybe we'll do it later. But it's interesting discussion. You can look at it when I upload the notes to Quarkus later. And we'll probably have to use it at some later point. But for now, let's move on to the second part of today's lecture, which is in the textbook. I forgot to write this here. Text section 2.3. And this will be about image and kernel. So we've now explored transformations a whole lot. We've talked about the correspondence matrices, and now we want to introduce two new things and then combine them all together. So let me start with a definition. And this definition is just the pre-image of a transformation, the kernel, and the image. Well, the pre-image of a certain subset of the target space is all the vectors in the domain that map into the space, into the subset S. So I think a graphical intuition is very helpful. If this is V and this is W, there might be a smaller like subset, maybe subspace, doesn't really matter for now, S. So this is just contained in W. Now every point in V maps somewhere in W. And if you only look at those that map into S, then this puts the condition on the elements in V. And this is exactly the condition that we want to use to define T inverse S as a subset of V. So some of these are all vectors that map into S. And by definition, T inverse of S is a subset in V. Okay, the next definition is the kernel. And this, if you look at this closely, it's a special case of the first definition, because what the kernel really is the pre-image of the zero vector space. This is the trivial subspace. So the kernel of a transformation is all the vectors that get sent to zero. And we've defined this in the very first week, in the very first lecture. But now we actually use this for transformations. So now, can you draw another picture? So if you have W, there's the origin, there's the zero vector. And for any transformation, every vector of V gets sent to W, and some of them might get set to zero. We already know that the zero vector gets sent to zero under every linear transformation. But this might not be the only one. So maybe there are more arrows coming from V that get sent to zero. So these all get sent to zero. And then this is going to be defined as the kernel of T. These arrows represent T sending vectors from V into W. Well, and the image of T is just the collection of vectors in the target space that get hit by some arrow. In words, I would say that these are all the vectors such that for some V in the domain, they are the image of this vector under T. I feel like I've talked a lot about this definition. Yes, some people call this range. This is correct. Any questions about this definition? Because I know what to focus on in my explanation. All right. I guess if there are any questions they might be solved by an example. So let's move to this example immediately. And let's look at the kernel and the images of some transformations that we've seen so far. We've seen the derivative from polynomials. And by definition, the kernel is just the ones that get sent to 0, which polynomials get sent to 0. Well, if p of x, if d by dx of p of x is 0, this means p of x is some constant. So this means that we could say that the kernel of d by dx is equal to all the polynomials in P and R, such that P of x is equal to C. What about the image? Oh, I already wrote this here. Okay, and you can also observe that if you have d by dx and you take the derivative of a maybe p0 plus p1x plus p2x squared all the way up to pn x to the n. If you take the derivative, what happens is that the p0 is just gone, and we have p1, we have the ith coefficient pi with one less power of talking and writing is really difficult actually. P1 plus 2 p2x and so on. You know what this is. N times pn x to the n minus 1. But now notice that the derivative of a degree n polynomial is degree n minus 1 polynomial. So this means that no degree n polynomial can be the derivative of a degree n polynomial. That's something that you all know, but just in this context, we can express this in terms of the image of the d by dx transformation. So this means, I mean, let me just write this down. This can't possibly be of degree n. But every polynomial of degree n minus 1 can be found. So if you tell me what the coefficients should be here, I'll be able to give you some polynomial on the left-hand side such that the derivative is what you proposed. Meaning that, long story short, what I want to say is that the image of d by dx is, and no, we started in PNR, so the image is Pn minus 1R inside PNR. Maybe let me add here that this was the transformation. No, maybe that's confusing. So the image will be the polynomials of degree n1. What about the evaluation map? I think this would have been an example that we skipped, but let me just tell you what the evaluation map is. So the evaluation map, EV sub 2, the evaluation map goes from polynomials. Oh, sorry, this is not to R. What does it do? Well, if you give this map polynomial p of x, it'll give back p at the value 2. For example, if you have the evaluation at 2 applied to 7x squared plus 5x, then this will be equal to, you just substitute 2 for x. So you're going to have 2 times 2 squared plus 5 times 2. So it's going to be 7 times 4 plus 10 is going to be 38. Did I spoil the answer? Yes, I did. Okay, so the question is, what is the kernel of this? The kernel of the evaluation map at 2 is by definition, and now we're using this the set notation. First of all, we have all the polynomials inside P and R. I'm running out of space. Let me move this away. Does it fit? Almost. Okay, so we have all the polynomials, but now the condition is that evaluation, it has to be sent to 0 by our transformation. Evaluation at 2 of P of x is 0. We can rewrite this condition into something, I mean, we can simplify this, that's what I mean. Meaning it's all the polynomials in P and R such that P of 2 is 0. And this is exactly what I wrote here. That's the polynomials that have a root at x equals 0. That's exactly what we just found out. And the image, can someone guess what the image is? Just write it, or yeah, it's R. Why is that? Because we can find, in particular, the constant polynomials, constant value c, will evaluate it to c. So for any constant in R, there's a polynomial that evaluates to this number. So the image of EV2 is equal to R for every real number c. There is P of x equals c, such that in particular P of 2 is just c. Okay, any questions before I shrink my... I want to make this fit next to this. Okay, so this was 1, this was 2. There's